Hello everyone. So, in last class we considered a parabolic equation and we have learned finite difference formulation to discretize these parabolic equations, and mostly we considered in last lecture this explicit method where only one unknown was there. So, in today's lecture we will consider the same parabolic equation and we will discretize this equation using implicit methods. So, today's is lecture 2 finite difference formulation of parabolic equations and we will learn implicit methods. So, this model governing equation whatever we considered, that is del phi by del t is equal to gamma del 2 phi by del x square. Okay. So, now we will use implicit methods. So, in implicit method you know that there will be more than one unknowns. Implicit method. Okay. The first method what we will learn that is known as backward time central space method. So, that is known as BTCS. So, backward time central space, so commonly known as BTCS method. Okay. So, that you can see that we will use that finite difference formulation for this first derivative as backward finite difference approximation, and the special second derivative what we have in the right hand side, that we will use central difference method. So, obviously, the order of accuracy will be first order in time and second order in space. So, you can see, so which way we will discretize this equation. So, del phi by del t will take phi I n plus 1. Okay. So, same thing, I is the grid index and the time level we are denoting with the superscript n or n plus 1, where you know that n is your previous time, okay, and n plus 1 is your present or current time. Okay, and the difference between this time is known as time step, and that is your delta t. So, delta t is your time step. Okay. So, this now we will use first order accurate scheme, which is your backward finite difference formulation for this first derivative with respect to time. So, that we have discretized. Now, gamma and central difference we will use, okay, in space. So, it will be phi I plus 1 minus 2 phi I plus phi I minus 1 divided by del x square. So, as it is backward in time, all these phi will take from the time level n plus 1, which is your present time. So, you can see that we have more than one unknowns, because at I plus 1 and I minus 1, at these discrete points we have unknown phi at time level n plus 1. So, if you see the grid points, so you can, so if this is your nth level grid and if it is n plus 1 level grid. So, this is your I, this is your I plus 1 and this is your I minus 1. So, this is obviously you have a uniform grid size. So, that is your delta x and this is your also delta x. So, it is at level n plus 1, obviously then we will have phi I at n plus 1, phi I plus 1 at n plus 1 and phi I minus 1 at n plus 1. Okay. So, this is the time level n plus 1 we are considering, okay, and nth level only one known values required. Okay. So, that is at point I and its value at phi I in time level. Okay. So, now all the unknowns you take in left hand side, and obviously there are 3 unknowns. So, you will get the algebraic equation like. So, if you define the diffusion factor, okay, which is known as gamma x as gamma delta t by delta x square. Okay. So, this is your known as diffusion factor or coefficient. So, gamma delta t by delta x square, and now we can write it as, so you can see phi I n plus 1 is equal to phi I n plus gamma x into phi I plus 1 n plus 1 minus 2 phi I n plus 1 plus phi I minus 1 n plus 1. Okay. So, all these n plus 1 time level you can take in left hand side. So, you can see phi I already in the left hand side it is there. Okay. So, in the left hand side of this algebraic equation you can see that phi I at time level n plus 1 is there. So, this is your term, and right hand side also you have phi I n plus 1s. Okay. So, now you can rearrange it and you can write it as gamma x. Okay. So, phi I minus 1 n plus 1. Okay. And if you now take phi I, so this we are taking in the left hand side, it will be so minus 1 plus 2 gamma x phi I at n plus 1. Okay. And you have another term plus gamma x phi I minus 1 sorry I plus 1 n plus 1. Okay. So, you will have in the then right hand side, as phi I will go this side. So, it will be minus phi I n. Okay. So, this is the final algebraic equation. So, at each discrete point you can write this algebraic equation. So, obviously, if you form the matrix, then you will get a tridiagonal matrix. Okay. So, for all the points, interior points, if you write this in a matrix format, then you will get tridiagonal matrix. Okay. Because you can see that you have phi I at n plus 1, okay, phi I plus 1 n plus 1 and phi I minus 1 at n plus 1. So, you can see that in the left hand side there are 3 unknowns, okay, at n plus 1 time level. So, that is your present time level where we need to find the values at n plus 1 time level, and 3 discrete points phi I minus 1 and phi I plus 1. Okay. So, here these 3 discrete points we need to find the value of phi. So, obviously, you can see it will form tridiagonal matrix, okay, and right hand side this value is known from the previous time level n, and obviously you can see this is your coefficients of this phi. So, it is gamma x, it is minus 1 plus 2 gamma x, and this is plus gamma x, and if you can form a tridiagonal matrix, okay, considering this equation at all grid points, then you will get a tridiagonal matrix, and it is easy to solve using TDMA, tridiagonal matrix algorithm, which is famously known as Thomas algorithm. So, if you see the stability analysis of this finite difference formulation, then solution is unconditionally stable. So, this is the advantage of this implicit method. So, it is unconditionally stable, unconditionally stable. Okay. So, that we will show later. And what is the order of accuracy? Order of accuracy is your delta t, okay, first order in time, and delta x square second order in space. Okay. So, this is a simplest method where 3 unknowns are there and easy to solve this equation, and it is sometime it is known as Larsonen method. So, sometime it is known as Larsonen method. Larsonen method, okay, and famously known as BTCS, okay, backward time central space method. So, obviously, you can see as it is implicit method, there is no time restriction, implicit method, and it is unconditionally stable. So, obviously, you do not have any time step restriction. Okay. So, delta t you can choose a larger value. Okay. But obviously, in terms of the accuracy there is some limitation, because if you choose higher delta t, obviously truncation error also will increase. Okay, because delta t tends to 0, then only the truncation error will tend to 0. So, obviously, you have some limitation in choosing the delta t, but you can go larger time step if you use implicit method. But in explicit method we have seen that there is some restriction where gamma x should be less than equal to half for this finite difference formulation of this equation. So, now we will modify this equation and we will get one finite difference formulation which is second order accurate in time and space. Okay, and popularly this scheme is known as Crank-Nicolson scheme. It is also implicit scheme and it is known as Crank-Nicolson scheme. So, Crank-Nicolson method, okay, or scheme. So, here whatever we have used in BTCS scheme, let us write first. BTCS we have used. So, what is the governing equation? It is del phi by del t gamma del 2 phi by del x square. So, in BTCS you have used phi I n plus 1 minus phi I n divided by delta t is equal to gamma into phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x square. Okay. So, this is your just BTCS scheme whatever we have discussed just now, and all these you are taking from n plus 1, n plus 1, n plus 1. Okay. So, here what we will do now, instead of taking this diffusion term, these dependent variables at n plus 1 time level, we will take the average of phi I n and phi I n plus 1. That means, the values of phi at nth time level and the n plus 1 time level. So, the average value you have to take. So, what we will take? So, this value we will take as phi I plus 1 plus phi I plus 1 at time level n plus 1 and n divided by 2. So, average value we are going to take. Similarly, for this point also we will take phi I plus phi I n plus 1 n divided by 2, and this also will take phi I minus 1 plus phi I minus 1 at n plus 1 and n by 2. So, now we are modifying this BTCS scheme. In the diffusion term, the value of phi which we took at n plus 1 time level, now we are taking an average value of phi n plus 1 and phi n at each discrete points. Okay. So, that we are taking. So, if you write this Crank-Nicolson method which is known also CN method. Okay. So, if you write it, so what you are going to get phi I n plus 1 minus phi I n divided by delta t is equal to. So, now we are replacing this as phi I plus 1 n plus 1 plus phi I plus 1 n divided by 2, okay, divided by delta x square minus 2 into phi I n plus 1 plus phi I n divided by 2 and plus phi I minus 1 plus phi I minus 1 n plus 1 n divided by 2. Okay. So, we have taken the average value. So, now you rearrange it. So, if you rearrange it in this manner, then you can see that you will get phi I n plus 1 minus phi I n divided by delta t is equal to. So, you can see that everywhere 2 is there. So, that you can take it outside gamma by 2. Okay. And you take all n plus 1 together. Okay. So, this term, this term, this term, and n term you write separately. Okay. Phi I n this and this. Okay. So, if you write it, then you will get phi I plus 1 n plus 1 minus 2 phi I n plus 1 and now this term. Okay. So, this is your phi I minus 1 n plus 1. Okay. So, now divided by delta x square. So, all the n plus 1 time level value we have taken together, and similarly we will take all nth time level these terms together. So, we will get phi I plus 1 n minus 2 phi I n plus phi I minus 1 n divided by delta x square. So, can you see or observe, can you observe something from this equation? Okay, you can see that this term is discretization like BTCS, okay, implicit method, whatever we have used backward time central space method. So, similar to that. So, it is similar to BTCS, okay, and you can see this all we have taken from the previous time level n, okay, which is actually explicit method, and we have used FTCS, forward time central space. So, it is kind of forward time central space method. So, it is, you can see Crank-Nicolson method when we are using. So, you can see when we are using the Crank-Nicolson method, it is some average of BTCS and FTCS, because right hand side if you see, okay, and observe, you see it is average 1 by 2, okay, and it is BTCS type discretization and it is FTCS type discretization. Why it is BTCS? Because all are at n plus 1 time level. You see these 3 discrete points I plus 1, I minus 1 or at the present time level n plus 1. So, it is kind of BTCS method, and this one you can see all these discrete point I plus 1, I and I minus 1, the value of phi at nth time level, and it is kind of explicit method whatever we learnt FTCS. So, similar to that. So, and 1 by 2 it is here. So, you can see it is average of BTCS and FTCS scheme. The advantage of this discretization is that it is a second order time accurate. Okay. Anyway, we are using central difference method in space. So, obviously, it is delta x square, but time level also it is delta t square. So, the accuracy is order of delta t square and delta x square. Okay. So, second order accurate both in time and space, okay, and it is unconditionally stable. So, if you do the stability analysis of this finite difference formulation, you will find that it is unconditionally stable. So, you do not have any restriction to choose the time step delta t. So, it is unconditionally stable. So, it is unconditionally stable. So, you can see that for this discretization method Crank-Nicolson, it is second order time accurate and unconditionally stable. So, how you can show that it is a second order time accurate? Okay. So, what method you can see now, you can view it as a 2 step methods, okay, 2 steps method. Okay. We are talking about only Crank-Nicolson method. Okay. So, now you can see as 2 step method. Let me write the equation first, del phi by del t is equal to gamma del 2 phi by del x square. Okay. So, this is your n to n plus half, okay, and n plus half to n plus 1. So, you are going in 2 steps from 0 to delta t. So, this is your delta t by 2, this is the time step delta t by 2, and this is also when you are going from n plus half to n plus 1, this is also del t by 2. Okay. So, now you see that this Crank-Nicolson method you can think as a 2 step methods. Okay. So, where you will use first from time level n to n plus half as FTCS, which is your explicit method, and from n plus half to n plus 1 you will consider as BTCS, which is your implicit method. So, you can see here. So, you are moving from n to n plus half and the time step is delta t by 2 and you use FTCS method here. Okay. And when you are moving from n plus half to n plus 1, so again the time step is delta t by 2 and you can use BTCS. okay, which is your implicit method. So, if you use that way, then you can discretize this model parabolic equation as, so first step, okay, so you are using FTCS scheme. So, how you can discretize? So, you are going from n to n plus half. So, it is n to n plus half divided by del t by 2. So, which is your time step is equal to, now right hand side you have gamma. So, this discretization is phi I plus 1 minus 2 phi I plus phi I minus 1 divided by del x square. Okay. So, this we are using FTCS. So, all will be at nth time level. Okay. So, if you see the grid points, okay, so here you can see, so at n to n plus half you are moving. So, now you use this as point I, this is your I plus 1, this is your I minus 1 and constant step size delta x you are using. Okay. So, the values of phi I at n you are using, phi I plus 1 at n you are using, and phi I at n minus 1 you are using, and from there you are calculating the value at phi I at n plus half. Okay. So, that from this discretization you are finding. Then in the second step, so in the second step now use BTCS. Okay. So, now you are moving from n plus half to n plus 1. So, obviously, when you are using BTCS, the spatial derivative all you will take from n plus 1 time level. So, it will be phi I n plus 1 minus phi I n plus half divided by del t by 2 is equal to gamma phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x square, and all you will take at n plus 1. So, all you will take from n plus 1 time level. So, this is your BTCS method you are using. Okay. So, now if you can see that if you simply add these two equations. Okay. So, if you add these two equations, what you will get? So, you see phi I n plus half, phi n plus half you will cancel out. So, if you say that this is your equation A and this is equation B, then adding equation A and B, what you will get? You see, you will get phi. So, phi I n plus half. So, these two will get cancelled. Okay. So, this phi I n plus half and this phi I n plus half will get cancelled. So, you will get phi I n plus 1 minus phi I n divided by del t by 2 is equal to gamma. So, you are adding it, simply you add it. So, phi I plus 1 n plus 1 minus 2 phi I n plus 1 plus phi I minus 1 n plus 1 divided by delta x square, okay, and phi I plus 1 minus 2 phi I plus phi I minus 1. So, this you at, so these you are taking from n plus 1 because this is you are writing. So, delta x square. Okay. So, now this half you can take it this side. So, it will be phi I n plus 1 minus phi I n divided by delta t. So, delta t we are taking here and half we are taking in the right hand side. So, you can write gamma by 2, okay, and phi I plus 1 minus 2 phi I plus phi I minus 1 divided by del x square. So, all at n plus 1 time level plus phi I plus 1 minus 2 phi I plus phi I minus 1 n delta x square. So, you can see that you can think this Crank-Nicholson method as a two-step computations. Okay. So, one computation you are doing from n to n plus half as FTCS, then n plus half to n plus 1 as BTCS scheme. So, you can see that obviously it is unconditionally stable, we have already discussed, and the order of accuracy is delta t square and delta x square. So, order of accuracy is delta t square and delta x square. Okay. So, we will show in today's lecture that this Crank-Nicholson method is second order accurate in time and space, but before that let us discuss another method which is known as beta scheme or beta method. Okay. So, this is a general form of finite difference equation of model equation del phi by del t is equal to gamma del 2 phi by del x square. So, our governing equation is del phi by del t is equal to gamma del 2 phi by del x square. Okay. So, obviously, we have different time level, one is n which is known as previous time level, this is your n plus 1, it is your current time level, and the time step is delta t, Okay. So, we will now use a general form to discretize this equation like this. So, we will discretize as phi I n plus 1 minus phi I n divided by delta t. So, the I discrete point obviously you can see that it will be your I, this is your I plus 1 and this is your I minus 1. Okay. So, the step size is constant, this is your delta x. Okay. Similarly, you have here phi I plus 1 which time level n, phi I n and phi I minus 1 n, and similarly at n plus 1 time level also you will have the discrete points I plus 1 and I minus 1. So, you have phi I n plus 1, phi I plus 1 n plus 1 and phi I minus 1 n plus 1. Okay. So, with this now if you discretize this equation using beta method, we will write in this. So, diffusion coefficient gamma, okay, then we will take a factor beta, okay, then we will take the implicit kind of discretization of this special derivative phi I plus 1 minus 2 phi I plus phi I minus 1, okay, divided by delta x square, and we will take this discretization at n plus 1 time level, n plus 1, and the remaining 1 minus beta will take in nth time level. Okay. So, it will be phi I plus 1 minus 2 phi I plus phi I minus 1 delta x square, okay, and all these at nth time level. Okay. So, what we have done in beta method, that we have taken a factor beta where beta times the del 2 phi by del x square discretization we have taken as a implicit manner. So, all these phi we have taken at n plus 1 time level, and the remaining 1 minus beta times the discretization of the special derivative del 2 phi by del x square, and all these dependent variables phi at discrete points I plus 1 and I minus 1 we have taken at the time level n. Okay. So, that is your previous time level. okay. And in the beta times we have taken the value of dependent variables at n plus 1 time level, which is your current time level. So, now you can see that it is a general method we have written in a factor, which is beta is a factor. Okay. So, now you can see if beta is equal to, if you put 1, then what you will get, and if put beta is equal to 0, what you will get, and if beta is equal to half, then what you will get. So, all these things already we have discussed. So, let us say that if you have beta is equal to 0, okay. So, if beta is equal to 0, then you can see the first term here. So, this first term will get 0 and you will get only the second term, and you will get in this form phi I n plus 1 minus phi I n divided by delta t is equal to gamma phi I plus 1 n minus 2 phi I n plus phi I minus 1 n divided by delta x square. So, what type of discretization it is? So, obviously only one unknown is there. So, it is FTCS, right, forward time and central space. So, explicit method, and it is known as FTCS. Okay. So, now if you put beta is equal to 1, okay, special cases we are just discussing. So, beta is equal to 1, then obviously you will get phi I n plus 1 minus phi I n divided by delta t is equal to gamma phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x square, and if beta is equal to 1, then this term will get 0. So, only this term will remain. So, you will get n plus 1. So, what is this discretization? So, this discretization is obviously implicit method, because more than one unknown is there, and commonly this method is known as BTCS, okay, backward time central space. So, it is implicit and it is known as BTCS. Okay. And if you put beta is equal to half, then you can see, okay, so if you beta is equal to half, then you are going to get phi I n plus 1 minus phi I n divided by delta t is equal to, so beta is equal to half, 1 minus half will be half. So, you take common gamma by 2, okay, half we have taken common. So, you will get phi I plus 1 n plus 1 minus 2 phi I n plus 1 plus phi I minus 1 n plus 1 divided by delta x square. Okay. So, now the second term you will get, so 1 minus beta half we have taken outside this bracket. So, I plus 1 n minus 2 phi I n plus phi I minus 1 n divided by delta x square. Okay. So, you know that it is Crank-Nicolson method. Okay. So, this is your Crank-Nicolson method. Okay. So, obviously you know that FTCS is conditionally stable, and the condition is gamma x should be less than equal to half, where BTCS is unconditionally stable, and also the Crank-Nicolson method is unconditionally stable. But FTCS and BTCS both are first order accurate in time and second order in space, but Crank-Nicolson is second order accurate in both time and space. So, it is order of delta t and delta x square. This is your order of del t and del x square, but Crank-Nicolson method is order of del t square and delta x square. So, you can see that it is a general method where we have used one beta factor, and with change of beta you can get different scheme which may be explicit or implicit or first order accurate or second order accurate depending on the value of beta. So, in general we can write for half less than equal to beta less than equal to 1, the method is unconditionally stable. Unconditionally stable, but if beta varies between less than half and greater than equal to 0, then the method is conditionally stable. Okay. So, now we will show that Crank-Nicholson method is second order accurate in time and space. So, how we will show, because from whatever discretization we have written here, from there you cannot easily tell that it is second order accurate in time. Obviously, space you can see that space you can say that it is second order accurate in space, but from this discretization of this time derivative, okay, easily you cannot say that it is a second order accurate in time. So, let us derive the truncation error, and from truncation error we will be able to find that what is the order of accuracy. So, truncation error, obviously you know the difference between the partial differential equation and the finite difference equation. Okay. So, now let us see it. Okay. So, what is the discretization of Crank-Nicholson method we have done? So, first let us write that. Okay. So, the equation is del phi by del t. So, this is your gamma del 2 phi by del x square. So, this is your partial differential equation, and what is your finite difference equation. So, after discretization, okay, using Crank-Nicholson method, whatever you get, that will be finite difference equation. So, that will be phi I n plus 1 minus phi I n divided by delta t is equal to gamma by 2. Okay. So, phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x square, and at time level let us say n plus 1, okay, and plus you have phi I plus 1 minus 2 phi I plus phi I minus 1, this is your n. Okay. So, this is your Crank-Nicholson method, already we have discussed in detail. So, now we want to find what is the truncation error. For that, what we will do, each dependent variable now we will expand using Taylor series. Okay. Then we will see the difference between this partial differential equation and the finite difference equation, then we will find the truncation error, and that will tell us that what is the accuracy of this scheme. So, now you see, if you say phi I plus 1 n plus 1. Okay. So, if you use Taylor series expansion, okay, of each dependent variable, okay, at particular discrete point and particular time level. So, you can see this is having I plus 1 and n plus 1, that means you have x plus delta x and t plus delta t. Okay. So, it is function of x and t both. Okay. So, x plus delta x and t plus delta t. So, now if you expand, so what you will get? So, you will get phi I n, okay, plus, so you can write del x del of del x plus del t del of del t phi, okay, obviously at level I and n. Then you can write 1 by factorial 2, okay. So, then it will be del x del of del x plus del t del of del t square, then phi I n and other higher order terms. Okay. So, we are not writing other terms. Okay. So, similarly you do for other, so now you write phi I n plus 1. Okay, so only it is t plus delta t and x, so it will be simple phi I n, okay, plus delta t, okay, del phi by del t, okay, at time level discrete point I and n, then plus del t square by factorial 2 del 2 phi by del t square, okay. Then you will get del t cube by factorial 3 del cube phi by del t cube I n and other higher order terms. Okay, so that we are not going to write, and okay, similarly you write phi I minus 1 and n plus 1. Similarly you write phi I minus 1 n plus 1. So, you will get phi I n plus, okay, so it is for phi I minus 1. So, it is x minus delta x and n plus 1 is t plus delta t. So, about x and t you are expanding. So, obviously you will get minus delta x, because you have delta minus delta x. So, del x plus del t del of del t, it is t plus delta t only. So, phi I n plus 1 by factorial 2. So, it will be minus delta x del of del x plus del t del of del t square phi I n plus higher order term. So, now the next we will expand phi I plus 1 n. Okay, so, whatever are there this dependent variables. Okay, so, phi I plus 1 n. So, here x plus delta x and t. So, x plus delta x only. So, it will be phi I n. So, delta x del phi by del x, okay, I n plus del x square by factorial 2 del 2 phi by del x square, okay, then plus del x cube by factorial 3 del cube phi by del x cube, okay, plus higher order term. Similarly, now we will write phi I minus 1 and n. Okay. So, now it is minus delta x, x minus delta x. So, it will be phi I n minus delta x del phi by del x plus delta x square by factorial 2 del 2 phi by del x square I n minus del x cube by factorial 3 del cube phi by del x cube I n plus higher order term. Okay, so, now we have expanded all these phi I plus 1, n plus 1 and whatever dependent variables are coming. So, you have expanded using Taylor series expansion. Now, let us put it in the finite difference equation. Okay. So, first let us consider only the left hand side. Okay. If you consider left hand side, then what is there in the left hand side of the finite difference equation. Okay. So, what you will get? Left hand side is phi I n plus 1 minus phi I n divided by delta t, right. So, what you can write from this second? So, from the second directly you can write, you can see from here. Okay. So, from here you can directly write phi I n plus 1 minus phi I n, okay, divided by delta t. So, it will be del phi by del t. Okay. We are not going to write I and n, because all the derivatives will be at the point discrete point I and the time level n. So, plus, so delta t you have divided. So, it will be delta t by 2 delta t by 2 del 2 phi by del t square, okay. Then plus you can see from there. So, delta t you have divided. So, it will be del t square divided by 6, okay, factorial 3 means 6. So, del cube phi by del t cube plus higher order term. So, in the left hand side we have already seen that only these terms will be there, and the right hand side you see. So, let us say this is your, let us say this term, okay, this term is 1 and this term is 2, okay, this term is 2. Okay. So, now you see in the right hand side, let us say the term 1, okay, term 1, okay, of term 1 of right hand side. So, what you are going to get? So, it is gamma by 2 phi I plus 1, and you can write delta x square also. So, you can write gamma by 2 delta x square, and you have phi I plus 1 minus 2 phi I plus phi I minus 1, which time level? In n. Okay. So, term 1, let us see what will happen. So, you take phi I plus 1 n, okay, so this one, then 2 phi I anyway it is there, and phi I minus 1 n. So, these two last two, this expansion you take and put it here. So, what you are going to get here? So, you are going to get here gamma by 2 delta x square, okay. So, phi I plus 1 n. So, already we have expanded using Taylor series. So, you put it there. So, it will be phi I n plus delta x del phi by del x plus delta x square by 2 del 2 phi by del x square plus del x cube by 6, okay, factorial 3 6 del cube phi by del x cube, okay, and other terms, higher order terms we are not writing, then minus. So, minus now 2 phi I, okay, minus 2 phi I. So, minus 2 phi I, okay, n, then you write phi I minus 1 n, the expansion whatever you have written. So, it will be plus phi I n minus delta x del phi by del x, okay, all these derivative about the point I and n. So, about discrete point I and the time level n. So, del x square by factorial 2 is 2 del 2 phi by del x square, then it will be minus del x cube by factorial 3. So, it will be 6. So, it will be del cube phi by del x cube, okay, del x cube, and another term you take here. So, it will be easy. So, it will be minus del x 4. So, what you will get next term? So, factorial 4. So, factorial 4, okay. So, factorial 4 means 24, right. So, it is 24 del 4 phi by del x 4, okay, plus higher order term, okay, and here also you write another term, okay. So, you write del x 4 by 24 del 4 phi by del x 4, okay, the other term, and minus 2 phi I n. Okay. So, now let us see. So, you can see that this is your phi I n, this is your phi n, 2 phi n, and it is minus 2 pi n. So, it is cancelled out. These will cancelled out, okay. These also will cancel out, plus and minus. So, whatever terms you have, let us write down here. So, you will get, so delta x square. So, delta x square you just divide with each term. So, you are going to get gamma by 2, okay. So, gamma by 2. So, you can see here 2 del 2 pi by del x square is there. So, 2 and divided by 2 is there. So, it will become, and delta x square will be cancelled out. So, you will get del 2 phi by del x square, okay. So, next you can see this term, okay. So, you have 2 into del x to the power 4 by 24 del 4 phi by del x to the power 4. So, if you 2 into this you write, then you will get, and delta x square will be, if you divide then it will be delta x square. So, it will be delta x square divided by 2 into 2 was that. So, it will be 12, okay, del 4 phi by del x 4, okay, and plus other higher order terms. So, that we are not writing. So, now in the first term in the right hand side we have done. Similarly, let us do the second term in the right hand side. So, let us do the second term. So, in the second term you can see this is phi n plus 1, okay, all n plus 1. So, you can write term 2, okay, of right hand side. So, it will be gamma by 2 and delta x square, if you take outside then it will be delta x square, and all at n plus 1 level, phi I plus 1 minus 2 phi I plus phi I minus 1 n plus 1 n plus 1 n plus 1. Okay. So, now whatever in earlier slide we have shown that this and this and this, okay. So, this expansion you put it there, okay. So, if you put it there, what you are going to get? So, you are going to get equal to, so it will be gamma by 2 delta x square, okay. I am just directly putting all these expansion in the last slide whatever we have shown, okay. So, you will get phi I n plus del x del phi by del x, okay, about point I and time level n. I am not going to write this, plus del t del phi by del t, okay, plus del x square by factorial 2 is 2, then del 2 phi by del x square, then you write del x into del t, okay. So, it will be del 2 phi by del x del t plus del t square by factorial 2 means 2, it will be del 2 phi by del t square, okay. Then another cube is there. So, that if you write it here you will get del x cube by factorial 3. So, factorial 3 is 6, you can write directly, del cube phi by del x cube, then plus del t cube by factorial 3 means 6, del cube phi by del t cube, okay. Then you will get 3 into del x square delta t divided by factorial 3. So, it will be 6, okay, it will be 6, then del cube phi by del x square del t, okay, plus 3 into del t square del x by factorial 3 means 6 you will write, and del cube phi by del x del t square and other higher order terms, okay. So, now this we have written the expansion for phi I plus 1 n plus 1. Now, the next term is minus 2 phi I n plus 1. So, that we are going to write the expansion. So, it will be multiplied by 2 because minus 2 phi I n is there. So, whatever you got, so minus 2 phi I n minus 2 delta t del phi by del t minus 2 delta t square by factorial 2 is 2 del 2 phi by del t square minus 2 into del t cube by factorial 3 means 6, okay. So, it will be del cube phi by del t cube and minus 2 into del t 4 by factorial 4. So, 24 del 4 phi by del t to the power 4. Okay. So, and other higher order terms. So, this is the expansion for phi I n plus 1. Now, let us write the expansion of phi I minus 1 at time level n plus 1. So, now let us write the expansion of phi I minus 1 n plus 1. So, you can write it as plus phi I n minus delta x del phi by del x plus del t del phi by del t plus del x square by factorial 2 means 2 del 2 phi by del x square. Okay. Then you will get minus del x del t del 2 phi by del x del t plus del t square by factorial 2 is 2 del 2 phi by del t square minus del x cube by factorial 3 is 6 del cube phi by del x cube plus del t cube by 6 factorial 3 6. So, del cube phi by del t cube plus 3 into del x square del t divided by factorial 3 is 6 del cube phi by del x square del t minus 3 into del x del t square divided by 6 del cube phi by del x del t square plus higher order term. Okay, so, now let us see that which are the terms are cancelled out. So, one is you can see this phi I n, this phi I n and this minus 2 phi I n. Okay, so, these are cancelled out. So, del x by del phi by del x, this is your plus and this is your minus. Okay. Then you can see this is del x del t and this is okay. So, this term and this term. So, this you can cancel. Then del t by del phi by del t, and so this is one term, okay, this is one term, this is one term, this is plus 2 and this is your minus. So, these you can cancel. Okay. Then you can see what are the other terms will be cancelled, you just check. Okay. So, you can see del t square by 2 del 2 phi by del t square. Okay. So, this term, this term and you can see this term. Okay. So, now these you can cancel out, okay, because this is minus 2. Then you have del x cube by 6. So, you can see this and this will cancel out. Then you will get 3 delta x t square. So, this term and this term will get cancelled. Okay. Then what are the remaining terms, let us see. So, you will get the remaining terms is this one is this. Okay. Then you have this term. Okay. Then you have this term, you have delta x square del 2 phi by del x square. So, this term, okay, and you can see this term also will get cancelled out. So, you can see this is your 6 actually. So, you can see this term, this term. So, it is 2 into this term and it is minus 2 into this term. So, this will get cancelled out. Okay. So, now you can see these are the 4 terms remaining from this expansion, and that we can write now is equal to, okay, gamma by 2 delta x square. Okay, first let us write, then it will be easy. So, you can see this delta x square by 2 delta x square by 2. So, there are 2. So, 2 times delta x square by 2 del 2 phi by del x square. Okay. So, this is also 2 times. So, you can write 2 into 3. Okay. So, 2 into 3 delta x square delta t by 6 del cube phi by del x square del t. Okay. So, and plus a higher order term we are neglecting. So, you can see you will get gamma by 2. Okay. So, it will be just so 2 will get cancelled out and delta x square. So, it is del 2 phi by del x square. Okay. So, this 3 will get cancelled out. So, you will get delta t only and del cube phi by del x square and delta t. Okay. So, now we have found the left hand side term and term 1 and term 2 in the right hand side. So, if you put all together, then what you are going to get. So, in the left hand side whatever you got, so you will get. So, we are now writing left hand side is equal to term 2, okay, of right hand side plus term 1 of right hand side. Okay. So, if you write it, then what you are going to get. So, left hand side you can see it is there is del phi by del t, okay, plus del t by 2 del 2 phi by del t square plus del t square by 6 del cube phi by del t cube. So, you can see this is the term, okay, we have written. Now, other two terms, okay, term 1 and term 2 whatever we have derived. So, let us write it equal to. So, it will be gamma by 2, okay, gamma by 2. So, what is there in the second term gamma by 2. So, it is del 2 phi by del x square del 2 phi by del x square, okay, plus del t del cube phi by del x square del t. Okay. This is the term 2 and what is term 1? It is also gamma by 2. Okay. So, gamma by 2. So, term 2 is, you see term 2 whatever we have written. So, this is the term 2. Okay. So, this if you write it here, so you are going to get del 2 phi by del x square plus delta x square by 12 del 4 phi by del x to the power 4 plus higher order term. Okay. So, now we have written this whatever from the expansion we have got. So, in the finite difference equation we put and we have written. Now, we will find the truncation error. So, you can see that our governing equation is del phi by del t is equal to gamma del 2 phi by del x square. Okay. Let us take the time derivative of this equation. Okay. So, del 2 phi by del t square you can write as gamma del 2 phi del x square del t. Okay. So, you can see that whatever term is there here that we can replace with del 2 phi by del t square. Okay. So, you replace it there. So, what you are going to get? So, del phi by del t by 2, okay, all you take in the right hand side. Okay. So, now you can see this is your gamma by 2 del 2 phi by del x square and it is gamma by 2 del 2 phi by del x square. So, it will be just gamma del 2 phi by del x square. Okay. So, that you can take in the left hand side. So, it will be minus. So, this is the, so you can see that gamma del 2 phi by del x square t is del 2 phi by del t square. So, you can write it as del t del 2 phi by del t square. Okay. So, the first term, this term we have written here, and so this is your del t by 2 because gamma by 2 is there. So, now you take it in the right hand side. So, it is be minus del t by 2 del 2 phi by del t square. Okay. So, you can see this will get cancelled out. Okay. And this if you take, and what is left here, you have gamma by 2. So, it will be plus gamma by 24 del 2 phi by del x to the power 4. Okay. This is there, and if you take this term in the minus del t square by 6 del cube phi by del t cube, okay, some other terms. Okay, so this get cancelled out. So, you can see that your governing equation is this one. So, that means del phi by del t is equal to gamma minus del 2 phi by del x square. Okay, so, this is equal to 0, but from the finite difference equation we got this additional term. So, this is your truncation error. So, now what is your truncation error? So, truncation error now okay. So, truncation error T e is gamma by 24. So, this delta x square will be there, here we missed delta x square. Okay, so, this term is coming here. So, del x to the power del x square. So, it will be del x square del 4 phi by del x to the power 4 minus del t square by 6 del cube phi by del t cube plus other higher order terms. Okay, so, now you can see the truncation error. So, the leading term what is there, delta x square and delta t square. Okay, so, the leading terms, okay, in the truncation error we have delta x square and delta t square. That means, the order of accuracy of this Crank-Nicolson scheme is delta x square and delta t square. So, we have proved it now. So, the accuracy is order of delta x square and delta t square. So, it is just truncation error we have found, which is the difference between the partial differential equation and the finite difference equation. So, first we discretize that equation, after that we expanded using Taylor series each dependent variable, then we put it in the finite difference equation, then the difference we have found as truncation error, and the leading terms you can see that it is delta x square and delta t square. So, obviously, you can see that Crank-Nicolson method is your Crank-Nicolson method is second order accurate in both time and space. Okay. Thank you.